And I'd like to introduce the breakup of bubbles in breaking waves. So now you're seeing an underwater view of this wave breaking process. As the crest is overturning more and more, it traps a long tube of air, which subsequently breaks to form bubbles of various sizes. And just to orientate you a little more, here's a top-down view of a similar wave. So bubbles are formed in abundance in these waves, and they span a wide range of sizes from micrometers to millimeters and even centimeters in the largest waves in the ocean. And they have a huge influence on acoustic propagation, light scattering, and the capture of carbon dioxide by the ocean. And just to highlight these influences, let me provide two key examples. So the first one you see here is better illustrated by another video of this aircraft carrier performing a rudder test. So it's turning at high speed, producing this long bubbly wake, many ship lengths behind the carrier. So this wake is formed because as the ship moves through the ocean, you can see it cuts and it generates waves to the side and back, which then break to form bubbles of various sizes. And the smallest bubbles in these waves, they take a long time to rise to the surface due to their low rise velocity, meaning that these wakes can stretch kilometers behind some of these fast and large ships. And it turns out that these wakes can be well detected using sonar as well as satellite imaging. So another example is the marine carbon cycle. Here I'm showing a schematic of how carbon dioxide is exchanged between the atmosphere and the ocean. So as you can see from this schematic, there are two main entrance points for carbon dioxide into the ocean, one of which is dissolution. So wave breaking enhances dissolution because it generates these large air pockets which break into smaller bubbles, which then dissolve and carry carbon dioxide with them into the ocean. It turns out that about 30 to 50% of the carbon dioxide that resides in the ocean comes from bubbles in general. But there is some uncertainty in this number because it is difficult to quantify the exact contribution of breaking waves. So doing this enhances our understanding of the marine carbon cycle with various practical implications, such as the acidification of oceans and biodiversity, as well as the generation of hurricanes and even the climate emergency itself. So the sizes of these bubbles have been measured in various experiments, including this one by Dean and Stokes in 2002. So they generated a 2-meter wave packet in their laboratory. And here I'm showing their size distribution. They were able to measure bubbles of sizes between 100 microns and 10 millimeters. And here you're seeing two distinct power law scalings, separated by a power law break at approximately 1 millimeter. So it was postulated that this power law break occurs at the Hinsey scale, where the Weber number of the bubble is approximately 1, meaning that capillary effects, which keep the bubble round, are approximately in balance with inertial effects, so energetic motions in the ocean. Above the Hinsey scale, inertial effects are dominant, and it is believed that turbulence generates a fragmentation cascade, which is further believed to generate a negative 10-thirds power law in the size distribution. Below the Hinsey scale, capillary effects dominate, but this negative 3/2 is in quotation marks because the experiments and simulations have not yet come to a consensus on how these bubbles are formed. So we'll leave these bubbles to the end, but we'll come back to these microbubbles in the last few slides. So right now, let's focus on this fragmentation cascade. So people believe that it exists, but there's still some uncertainty around it, which I will describe later. So the key question to ask today is, how are these bubbles formed? Or more precisely, does the formation of these bubbles actually satisfy the properties of a cascade? Or have we been misled all along? To carry out this investigation, we ran several simulations of a 27-centimeter water wave, so slightly smaller than the 2-meter waves of the experiments, and we used a grid resolution of 1 millimeter, so somewhere on the order of the Hinsey scale. So I'm about to show you how this simulation evolves, and what you're seeing here is the interface between air and water. So the wave breaks, as I mentioned, and trapping this tube of air, as you saw in the first video today. It breaks to form various bubbles, and the smallest bubbles persist, as I alluded to in the second video we saw today. So we let this animation replay itself. And it turns out that the largest bubbles in the system, so to the right of the experimental power law break, are generated by the turbulent breakout of these large air cavities over here, including this tube we saw earlier. And the smallest bubbles in the wave are generated, well, we believe that they are generated by free surface collisions, which form microbubbles. So as I mentioned, we'll leave this to the end. Right now, we'll focus on the super Kinsey scale bubbles. So what do we know about their formation? I kind of went through this briefly in a graphical manner, but let's be a bit more systematic now. So first, the critical length scale, where turbulent breakup terminates, was identified by Kolmogorov in 1949 and Kinsey in 1955, and is now known as the Kinsey scale. But it was only much later that more circumstantial support for breakup cascade was obtained, namely the negative 10-thirds power law scaling and the size distribution I highlighted earlier. So it was hypothesized by Garrett and others in 2000 based on dimensional arguments and experimentally and numerically observed, as I also mentioned earlier. So it seems like there's decent evidence for this scaling, but it turns out reality is a little more complicated than this. More recent simulations observe similar power law scalings, but were able to attribute it to other causes. Furthermore, several experiments earlier in time who ran similar breaking waves did not observe this power law scaling. So it seems like there's evidence for and against this scaling, which leads us to wonder if there is actually a cascade or not. So in this work, we seek more direct evidence of the breakup cascade to say more definitively if it exists or it doesn't. So with this in mind, here are the objectives and methodology of this study. We would like to construct a theory for bubble breakup because we want to use this theory to formally prove the existence of this cascade. And as I will mention later, we rely on the argument that the bubble mass transfer from large to small sizes has to be size local. So I'll explain cascade and locality later, but just to briefly describe this, locality means that this transfer of bubble mass across a certain cutoff primarily depends on the statistics of bubbles of sizes close to this cutoff, so a confined region of influence. But I'll explain this in more detail later. And then we use simulations to check if this theory is sound. We generate breakup statistics and use them to investigate breakup mechanisms, even beyond the regimes where we expect the theory to be completely valid. So here's the outline for today's talk. I'll first describe the theory for this bubble breakup. We'll examine this theory using simulations. And at the end, I'll briefly describe how we can apply the lessons learned in this framework, in this toolkit, if you would like, to enable future larger scale simulations. So I've placed these icons on the left just as a visual guide. And let's focus on the first section now. So two key questions we want to address. First, what is a breakup cascade? And second, how do we determine if this cascade exists? So I promised that we'll explain this term cascade. So let's go into this right now in this context of a turbulent energy cascade, because this is where the word cascade has been used most frequently to date. So it turns out that Richardson wrote this poem in 1920, saying that big walls have little walls that feed on their velocity, and little walls have lesser walls, and so on to viscosity. So the schematic on the left depicts the process described in this poem. So the top of the schematic represents large scales, the bottom represents small scales. So what is being described here is that energy is injected at the large scales, the energy containing scales. So there's a velocity that he's referring to. Then it is transferred, cascaded to smaller and smaller scales, from big to little and little to lesser. And then it is dissipated at the viscous scales. So that's the viscosity he's talking about. So the main theme here is a transfer process, in this case of kinetic energy, turbulent kinetic energy, from large to small scales. And just as an aside, I just want to mention that in a turbulent flow, we expect the large and small scales to be well separated, meaning that the small scales have to be much smaller than the large scales. This enables the appearance of a size invariant intermediate range where transfer occurs and a formal emergence of a cascade. But we'll come to this later. And just to give you a physical sense, because everything here has been rather abstract in scale space, let me just quickly show a schematic by Da Vinci in 1510. So what I'm basically saying is that the small scale motions coexist with large scale motions, and there's sort of a waterfall depicting this process. But moving on, so to use more formal terminology, energy is injected at the integral scales. And because inertial effects are dominant here, the non-linearity of the system cascades the energy to the Kolmogorov scale, where viscous effects come into play and dissipate the energy as heat. And just to give you a physical sense of what the scales are like, in breaking waves, the integral scale typically is on the order of 1 to 10 meters, or even larger in, say, rogue waves in the ocean. And the Kolmogorov scale is approximately 10 microns. And just to be a little more specific, here is a quantitative expression for the Kolmogorov scale. So in a bubbly flow, we expect that Lk depends on the liquid viscosity, the liquid density, as well as epsilon, which is the injection rate, the cascade rate, and the dissipation rate in this picture of the energy cascade. So most of this has been relevant to a single phase flow, or at least one with very few bubbles. Now let's bring in multi-phase flows into the picture. So as I mentioned earlier, the Hinze scale is approximately 1 millimeter. And to be more precise, here is a well-known expression for the Hinze scale. So if you look, these two expressions, well, they look very similar, except that the rho viscosity plays for the Kolmogorov scale is the rho surface tension plays for the Hinze scale. So if you believe, and people do, that turbulent kinetic energy is cascaded from the integral scales to the Kolmogorov scale, could we then postulate in parallel a bubble mass cascade carrying gaseous mass in bubbles from large sizes at the integral scale to small sizes at the Hinze scale? So this is perhaps the first takeaway of this theoretical section. We hypothesize that a breakup cascade exists, transferring bubble mass from large to small sizes in parallel with the energy cascade. So these two cascades happen together. And just to give you a sense, well, of what this bubble mass transfer is like, how do we quantify it? Let's dive into the cascade rate. So as you noticed earlier, I emphasized that epsilon is the cascade rate for the energy cascade. And correspondingly, we're interested in this quantity, WB, the bubble mass cascade rate. And just to underscore the importance of these two rates, I just wanted to mention as another aside that if we assume the size distribution, for F, scales, well, depends on these two cascade rates as well as the bubble size, we can show immediately from dimensional analysis that F would then scale as d to the negative 10ths. So this scaling I've been mentioning many times. But let's focus on WB for now. So we're interested in quantifying WB. And we want to interpret this as a flux across a certain cutoff size d. And we want to obtain an average quantification of this mass transfer because all cascades should be interpreted in average sense. So we are interested in the bubble mass, beginning from bubbles of sizes larger than the cutoff being transferred to bubbles of sizes smaller than this cutoff. So let's go ahead and quantify this flux. Let's start from a single event, just to keep things simple. So we have a cutoff size d over here, we have a parent bubble larger than the cutoff, and let's suppose that there are two children bubbles formed by this event. Since both children bubbles are smaller than the cutoff, there are two contributions to the bubble mass transfer. But one could easily imagine another event where only one of the children bubbles is smaller than the cutoff. Then in this case, there is only one contribution to the bubble mass flux. So if we carefully do this accounting over all the breakup events in the system, add everything together, then we can recover WB, this quantity we are interested in, the average transfer of bubble mass from large sizes to small sizes. So the next takeaway, we have defined this bubble mass transfer by adding the contributions over all the events in a single wave. And I'll come to this later. But if we have an ensemble of simulations, we can also average over all the realizations in this ensemble. So I've mentioned several times that the cascade is a transfer from large to small scales. But I never really talked about how this transfer actually occurs. So let's consider two mental pictures for this process. Let's consider this first, a systematic transfer of bubble mass from a large size to a slightly smaller size to a slightly smaller size, and so on and so forth. We call this process local. And just remember that each of these green arrows represents the aggregate transfer over many events and not just a single event. So let's focus on the middle arrow and let's put a cutoff across it. So what we're saying here is that for the flux crossing this cutoff, most of it originates at a size just larger than the cutoff and terminates at a size just slightly smaller than the cutoff. But one could imagine a more haphazard transfer of mass as well, leaking from one size to totally different size. And we call this process leaky. And so most fluxes are somewhere in between the two. So you can interpret this as a spectrum between locality and leakiness. But if we will consider a cascade in its stricter sense, so we go back to this reference by Lumley in 1992 below, and we use this term a spectral pipeline. So no accumulation, no disappearance, no interruption. So literally imagine a rigid hollow pipe channeling bubble mass from one end to the other. In this strict sense, a cascade should be local. But of course, reality is complicated, and as I mentioned, most fluxes lie in between these two extremes. So how do we measure the degree of locality of a leaky flux, since we need to know this to determine if a cascade exists or not? So again, let's consider this cutoff. We have contributions to this flux across this cutoff from various bubble sizes. How do we show that most of the contributions are confined to bubbles near this cutoff? So what we can do is decompose this flux into its differential contributions, into a Riemann sum. So going back to Calculus 101, we decompose WB as an integral over various bubble sizes. And we can perform this integral in two complementary ways. We can do this by decomposing the contributions from individual parent sizes, from D to infinity. So if we call this integrand IP, if we can integrate IP from D to infinity to recover the total flux WB, then for locality to occur, IP has to strongly decay as you go from D to infinity. So as you can see from this schematic, everything is bunched near the cutoff. So one function that satisfies this is a negative power law scaling. IP should take a negative power law scaling, meaning that contributions from much larger bubbles are minimal. And we'll use this shorthand infrared locality because infrared light has a larger wavelength than visible light. But just to summarize, strong locality, negative power law scaling in IP. So we can consider the process by symmetry in opposite fashion. We consider the contributions to individual child bubble sizes. So if we call this integrand IC, integrating this from 0 to D to recover the total flux, then IC needs to have a positive power law scaling. And we call IC ultraviolet locality. So to emphasize again, strong locality, negative power law scaling in IP, positive power law scaling in IC. And I'm repeating this many times because we will come back to these two quantities specifically when we discuss the simulations. So next takeaway, we hypothesize that in a strict sense, the cascade rate has to be size local, meaning that contributions to the flux should not come from bubbles far away from the cutoff. So I mentioned these two quantities, IP and IC. How do we actually quantify it? How do we evaluate it from the system? It turns out we can do this two different ways. We can measure this quantity directly from simulations or experiments, and I'll show how this is done later. Or it turns out, if we begin from some simple theoretical assumptions, and if we have an expression for WB, we can substitute these assumptions into WB and derive theoretical scalings for IP and IC. So this does involve some math. I'll quickly walk you through this derivation just to give you a flavor of how this can be done. So we begin with a single event again. And remember that the contributions to the flux depend on the size of the child bubble relative to the cutoff. We can express this mathematically as the following: an integral with respect to QB. The probability distribution of a child bubble size conditioned on a single parent size. So this was for a single event in a single parent size. So to extend this to the entire system, we multiply this by the number of parent bubbles. So this is F, the size distribution. Then multiply this by how often the event occurs. So GB, the breakup frequency. And because all this was of a single size, we integrate the contributions over all parent sizes larger than the cutoff to obtain this complete expression for WB. And I just wanted to emphasize that this expression is valid for any drop or bubble breakup system. But today, we're interested in turbulent breaking waves. So is it possible for us to begin with theoretical assumptions, turbulent flow scalings from single-phase turbulence theory, substitute them into this expression for WB above to derive theoretical scalings for locality? And it turns out the answer is yes, because W, as you see here, is an integral, can be expressed the integral over dc and dp. So it turns out that these scalings give us scaling of d to the negative 7 for IP and d to the 5 for IC. So negative power law scaling, positive power law scaling, meaning that a turbulent breakup process is indeed strongly local. And just to reiterate how this derivation is done, we begin with turbulent flow scalings for the size distribution F and the breakup frequency GB, which are themselves indirect measures of a cascade that others have used. We pair this with an assumption on the breakup probability QB, and by doing so, we can obtain theoretical scalings for IP and IC, which are themselves direct measures of a cascade. So to summarize this theoretical section, we hypothesize the presence of a breakup cascade. We claim that in a strict sense, this cascade should be local. We were able to quantify this bubble mass transfer, and we can measure it directly in simulation or experiments. But if we go one step further, assume some theoretical scalings from turbulence theory, substitute them into an expression for WB, we can prove theoretically that the turbulent breakup process is strongly local. And because these 5 characteristics are shown then to be self-consistent with one another, we can deem these 5 characteristics of a breakup cascade, which we will subsequently examine in simulations. But I just wanted to emphasize again that if in doubt, if these 5 tell us different things, then the last 2 quantities are sort of the deal breaker, because these are direct measures of locality. So next, I'll move on to the simulations. And again, we have 2 key questions we want to address today. First, do the simulation results support this theory I just described? And second, do the simulation results always support this theory? Or do the breakup dynamics evolve as the wave progresses? So let me first describe the solver and algorithms we used to start this off. So we ran 2 ensembles of a 27 centimeter wave. On the top right corner, you see this video. And you can see from the video that things are statistically unsteady, meaning that we cannot blindly time average statistics over the entire wave breaking process to converge our statistics. We have to consider the statistics at individual time snapshots. So this means that to obtain statistical convergence, we have to rely on ensemble averaging. So to do this, we ran 2 ensembles, a baseline ensemble with 30 realizations, which is our workhorse for today, and a more resolved ensemble with twice the resolution for mesh sensitivity study. Here are some details below on the domain and the solver, but let me just dive into the characteristics of the solver a little more. So we use the volume of fluid stream to ensure that mass is conserved. This schematic over here shows how the interface is represented in such a scheme. The interface is discontinuous, and this I'm plotting phi, the volume fraction field, going from 0 to 1 in each cell. But this discontinuity allows mass to be conserved, which is crucial because we are looking at the bubble size distribution. We use an unstructured code to enable a non-uniform mesh. In our case, we can cluster the points around where all the action is taking place. The solver has consistent mass and momentum transport, meaning that mass and momentum are vectored in exactly the same way. This allows stability and accuracy in these energetic air-water flows. And lastly, we use a balanced force algorithm for surface tension, meaning that all the forces are exactly balanced at the interface. This minimizes spurious currents of capillary origin. And this solver has been used to simulate a variety of two-phase flows. In this video, I'm showing jet atomization in a fuel injector. And you can see the formation of droplets as it progresses. So in addition to this solver, we also added two algorithms to sort of enable our computations later. So first, an identification algorithm. We picked an existing algorithm and we refined it to distinguish physical bubbles from spurious bubbles. So what do I mean by this? Here's an example of one of these spurious bubbles. So this picture was taken late in the wave breaking process. The interface is almost flat. There should be no large bubbles in the system. But yet the original algorithm picked up one of these large bubbles. So what's actually happening here is that the algorithm clumps together small pieces of air together, stitching them together to form this bubble that doesn't exist. And it turns out that bubbles like these have an impact on the size distribution. It does impact the entire distribution, but let me just categorize the errors into two limits. First, the subgrid bubbles. So this vertical line you're seeing here is the grid resolution. And you see the formation of these subgrid bubbles. So basically 1 to 2 cells with a little bit of air added together, forming these bubbles that don't actually exist in the system. So that's what you're seeing on the left. On the right, it turns out that these pieces of air also increase the volumes of all resolved bubbles. So it turns out that some of the largest bubbles in the system end up having higher volumes, putting them off the axis in this plot. So we refined the algorithm, corrected this algorithm, corrected the distribution, and here I'm plotting a distribution that we can rely more on because we know that the algorithm used to compute it can sort of fix these errors. The second algorithm we developed is a tracking algorithm. We came out of this from scratch to detect breakup and coalescence events, even though I'll just focus on breakup today. Using these volumes and centroids that were obtained from the algorithm we saw earlier, the identification algorithm. So this is just a video showing a toy problem, a drop in a Taylor green vortex breaking up into multiple drops. So we are able to identify the centroids and even volumes represented by these red dots, but we don't really know which bubble has broken up into which other bubbles. So we use this algorithm to construct these bubble lineages to find out who are the parent bubbles, who are the children bubbles, link everything together in a single family tree. And this family tree allows us to compute breakup statistics that I mentioned earlier, such as G, Q, I, and so on. So with these in hand, let us now move to the statistics. Let me first show you a macroscopic statistic, the bubble mass flux, WB. So I'm showing here is evolution over time. And you can see that the flux is initially quasi-steady. So it oscillates a little, but more or less it hovers around a mean value. And it eventually increases with time. Just to give you a physical sense of what's going on, here I'm showing the void fraction plot. You can treat this as a span-wise cut, a span-wise view of the wave. So before this entire time window, the wave is still in the process of entraining air, and all the bubbles are accumulated in this green region over here. At the end of this time window, the interface has sort of relaxed, and now the bubbles are more diffusely distributed beneath the wave. So this is sort of a static picture, which might still be hard to understand. So let me show you some videos as well. First, I'll show you a video of what's happening in this first purple region. The wave is still entraining air, and large bubbles are beginning to break into smaller bubbles. Now I'll show you a video of the second interval, this brown region. Now entrainment has more or less stopped, but large bubbles are still continuing to break into smaller bubbles, resulting in this increasing flux. So with this information in hand, what we're actually going to do is to time average the statistics over each of these two intervals, because we know that the characteristics of the breakup are so different in both intervals. So by doing this restricted time averaging, we can sort of contrast the behavior between these two phases. So let's focus on the early stages for now. So on the top, I'm plotting the results we expect from the theory. On the bottom, I'm plotting the simulation results. So some of the plots are a little small, but I'll zoom into some of them individually later to give you a sense of what's going on. What I just want to mention here is that in the early stages, we obtain agreement between the theory and the simulations for all 5 characteristics of the breakup cascade. And just to give you a sense of what this agreement is like, let's look at the size distribution specifically. So here I'm plotting the distribution from both ensembles. The 2 lines represent the 2 grid resolutions. The yellow dashed line represents the theoretical scaling. So you see agreement between all 3 in this intermediate range of sizes, which will be highlighted in the blue box in later plots. So this tells us 2 things. One, that the results I'm presenting today are mesh insensitive. And second, that the simulations agree with the theoretical scaling, which was also recovered by the experiments from Dean and Stokes and these 2 simulations over here. But let's just look at this quantity IT, just to see if there are some small deviations from the theory. So if you recall, this is the contribution from individual parent sizes, as you see in this schematic over here, relative to this cutoff. So I'm plotting the same thing here, except in logarithmic axis, and the cutoff is by this yellow dashed line. So you can see that close to the cutoff, this theoretical scaling of t to the -7 is almost recovered within error. However, you also see this long tail over here. So non-local events contributing to these dynamics, even though these contributions are small because they are 2 orders of magnitude smaller than the peak. Now let's just see what these points correspond to. What's actually happening here is that a large parent bubble is breaking into a slightly smaller parent bubble and a very small, a slightly smaller child bubble and a very small bubble. So in this case, there is only 1 child bubble smaller than a cutoff. So this volume over here is the only contribution to the bubble mass flux. This is why these points are so much lower than the peak. Nevertheless, these events still occur, and we return to them right at the end of the presentation. For now, let's move to the second time interval, where the flux is accelerating with time. So again, I'm plotting the theory on top, simulations below. This time, we have agreement for 4 of the 5 characteristics. So let's look at the size distribution in a little more detail. Again, this is time average over the second interval. So now we only recover a -8/3 power law scaling in the size distribution instead of -10/3. And to be honest, we don't know the full reason for this, except perhaps to hypothesize that coalescence is playing a larger role at these late times. What we can say more definitively is the steepening of the distribution at larger sizes. Because the exponent at these large sizes is -2 steeper than the exponent at intermediate sizes, we can say definitively that buoyancy is at play here. Specifically, these large bubbles are rising to the surface more quickly, disappearing more quickly, and thus tilting this distribution downwards because they are disappearing from the system. And I just wanted to emphasize that these 2 scalings over here were also recovered by these experiments and simulations highlighted in red. So just to recap, the left is the distribution from the first interval, the right the distribution from the second interval. The negative tented scaling, which many people have sort of defined this as a cascade, ceases to be adequate at late times because other mechanisms start to enter the picture. So the natural question to ask here then is there a cascade at late times since the distribution is changing? So it turns out that we can say a little more about this because we're able to directly measure these characteristics of a cascade. So let's now look at these two quantities, infrared and ultraviolet locality. So on the left, I'm plotting the contributions to individual child bubble sizes. On the right, the contributions from individual parent bubble sizes. So you see that the simulation and theoretical exponents do look similar, but let's not focus on that. Now, let's just say that the left plot has a positive power law scaling and the right plot has a negative power law scaling. So with this information alone, this tells us definitively that strong locality is observed in the breakup dynamics, even though we didn't see a negative tented scaling in the size distribution. In other words, yes, there is a cascade, even at these late times. So just to summarize this simulation results, we observed two characteristic intervals in the evolution of the flux. While the flux was quasi-steady, we observed good agreement between the simulations and the theory, lending strong support to the presence of a cascade, except for this presence of intermittent non-local events, which do not affect the net locality of the dynamics. Later, when the flux is increasing with time, the scaling for the size distribution does evolve, but we still observe size local breakup, telling us that cascade-like behavior still persists in the system. And perhaps the most important takeaway is that we are able to make this statement definitively because we can directly measure locality in this bubble mass flux. I just wanted to end by saying that, in fact, this procedure can be applied to other drop and bubbly flows. Nothing is restricting this to turbulent breaking waves. So in other words, we have an analysis toolbox for breakup and coalescence in generic two-phase flows. So I could stop here and end this, but it turns out that we can also learn some lessons from these results and see if we can apply them to enable future larger scale simulations. So I had this cryptic remark earlier saying that the large and small scales have to be well separated in a cascade. Let's see what this means in the context of locality. So it turns out that we know the large scales are influenced by the flow geometry, and locality sort of screens the small scales from direct effects of the large scales. This tells us that the small scales are universal, and this term is little loaded, so let me explain it a little more. What I mean here is that the small scales, the details of the small scales evolve independently of the details of the large scales. So this enables us to use universal subgrid-scale models to model the behavior of the small scales, meaning that if I set the grid scale in between the small and large scales, I can apply a universal model in this region. And again, let me be a bit more precise. What I mean is that you can use the same model and apply it to a few turbulent bubbly flows, including breaking waves. If not all of them, at least some of them. And we take direct inspiration from single-phase turbulence. We resolve the large scales, model the small scales, connect the two with the flux from large to small scales, in our case, the bubble mass flux WB, and we can implement this in a solver using its proxy GB, the breakup frequency. So this, again, could be the end of the story, but remember the occurrence of these non-local events I mentioned earlier. So what are the implications of this non-locality? It turns out that if we want to fully capture bubble breakup in these waves, we need another subgrid-scale model that bypasses this cascade. And we don't have too much time, so let me just quickly go through how we could implement this. So we can detect collisions in these breaking waves. And we can map these collisions to the impact of a drop on a flat surface. Because we know from experimental evidence that the right plot, the right model problem produces microbubbles. And this is feasible because we were able to implement a collision detection algorithm in this unstructured volume of fluid solver. So here I'm showing this red flashing dots just depict where the collisions are taking place and where microbubbles are expected to be produced, so not just any collision. With this collision detection algorithm, we can now span a wide range of scales. What do I mean by this? We have a simulation of a 10-meter wave. We detect collisions of characteristic scales of a millimeter, which by the way is also where we expect the grid resolution to be. We map this to a model problem where 1 millimeter drop is impacting a surface. And then we see what microbubbles are produced of sizes about 1 microns. Then we inject these microbubbles back into the large wave. So this allows us to spend 6 to 7 orders of magnitude in a single simulation. So with multiple subgrid-scale models, we can now handle multiple breakup mechanisms. And all this because we understand what is going on in terms of the breakup of bubbles in these breaking waves. So in turbulent breaking waves, large bubbles break into small bubbles via a cascade, and even bubbly flows in general, because we have shown that the flux is strongly local, both theoretically and numerically. And this locality tells us that the cascade is universal. And this universality lends legitimacy to the idea of subgrid scale modeling based on a cascade. And as I mentioned in the last few slides, it doesn't matter if the situation is more complicated. You can always add additional subgrid scale models to account for multiple breakup mechanisms in bubbly flows. With that, thank you all for coming to this talk today. Last but not least, I'd like to acknowledge my sponsors, A-Star and Stanford, and institutional support from ONR and DOE, who also contributed to computing time, such as this video you're seeing here. So this concludes my talk. Thank you all for coming, and I welcome any questions.